All right, you guys, so now that we've studied or have a definition for relations and functions, let's go ahead and take a look at some situations and try to determine if they are functional or not. What you'll notice is I have several different ways again to represent a relation. What you're seeing at the top end is what I call a schematic or a drawing. So what the arrows are kind of pointing out, here's your input set, A, B, C, and D, and here's your output set 1, 2, 3. So we can kind of see schematically where the inputs are going, the output. So the rule, right, is basically defined by the lines, if you would. And then, of course, the rule here is defined as a table, right? These x's are going to these y's. Here, these t's are going to these p's, right? So first column, second column, kind of keeping up with the x and the y. And then we have some ordered pairs, which are essentially just table of values, really, if you want. And then we actually have some equations, right? So again, this is mathematics. So a relationship between x and y, right, is shown in a relationship and equation, right? Down here we have a relationship between h and t, right, and a relationship. So given these relationships, which one of these are functions? And again, remember, a very nice tight way to represent a function, right, is the idea that one in creates one out, right, rather than, that whole definition. That's basically what a function is. One input can create only one output. If that's the case, we're functional. If it's not, then we're not. So let's go to work here. So part A here, if I look at it, right, so far A, right, the input of A goes exactly to 2. So one thing in, one thing out. So far, so good. But B has two lines, right? B has an output of 1, and B also has an output of 3. And so that guy right there kind of ruins it for everybody, all right? You take away B, we're functional. Everybody's going to just one thing. But since B goes to 2, right, this is not a function. Input B has two outputs. So there is a good justification why, right, that's not a function. It fails the definition, right, because one thing in only gives one thing out. In this case, the input of B has two outputs, not functional, all right? And so that is how you should answer your questions on a quiz or on your homework or whatever the case might be when you're determining whether something is not a function. Tell me it's not, tell me why. The next one, right, again, looking at the arrows, this is basically my input set and output set. So the input of E goes to only one output, right, omega. The input F only goes to one output, alpha. The input G only goes to omega as well. So one thing in, one thing out. One thing in, one thing out. One thing in, one thing out, right? And I guess beta just isn't involved or in some case, and that actually is going to impact something else. But this is a function, right? It satisfies the one in, one out, right? So that's basically it. Give me a letter, A and F, G, and it gives me one output, right, per letter. So that is very, very functional. Okay, and yes, it is okay for two inputs to go to the same output, right? We're just looking again, one in, one out. So for E, the output's omega, right? One in, one out. For G, it also goes to omega, but we're still talking about one in, one out. So repetition has nothing to do with it, right? It's, can I put something in and how many things come out? If one thing in and one thing out, it's a function. If there is something that has more than one output, it's not. That's how you determine that. Okay, so look at this table of values, right? So that's our next one. Is it functional or not? And the first thing I notice, right, is that there's an input of 3 occurring twice, right? And in both cases, right, the output's the same. So I'm going to say that this is not a function right away. It doesn't really matter what anybody else does, right? The input 3 has 2 outputs, and that fails our test of a functionality. All right, one thing in, one thing out. 3 ruins it for everybody as far as functions are concerned. So that is not a function. Over here we see 0. Again, treat this as x and y. Be consistent in terms of ordered pairs. X is always first, horizontal, right, and then vertical. So dependent, excuse me, the dependent and the independent variable. So I'm just kind of playing around with the variables to keep the structure going. First column is independent, x. Second column is dependent, y. 0 goes to 20, one thing in, one thing out. 50 goes to 60, one thing in, one thing out. 100 goes to itself, but that's still one thing in, one thing out, right? 150 goes to 60. Again, somebody's already gone to 60, but it's okay to go to the same spot, right? What's important is the input of 150 only has one output. 200 goes to 20, right? So did 0, but again, it's not how many things repeat. Repetition has nothing to do with it. You need to get that out of your language. You're basically looking, does each input go to exactly one output? In this case, the answer is yes. So this is a function. It satisfies the definition. One in, one out. All right, so nice and satisfied there. Looking at the next round, again, if you can see it in this, that's great. If you don't really see it, I'd recommend putting it in a table, right? We have 1, 2, 2, 4, 3, 5, 4, 4, and 5, 8. So maybe seeing it visually in that table, right? We can see that each input goes exactly to one piece of output. So this is a function. One in, one out. We're satisfied. Okay. Same thing here again. If you're having trouble visualizing it, I would just put it into a table of values. That way we can kind of see that. So we got -2, 0, -1, 2. So far so good. 0, 5. So far so good. We have 1, -2, and then we have 0, 8. And there's the problem right there, right? So this is not a function. Input of 0 has two outputs. And so that creates a non-function situation, right? So again, one thing in, one thing out is what we're looking for, and that relationship in F fails it. So it's a relation, but not a functional relationship. Okay? So getting to harder things, right? What happens if we don't have something nice and visual? We're only given an equation. Well, remember from our graphing days, right? All we're basically doing is putting something in. X is the input, right? And Y is the output. So basically we can test this, right? So how about we let X equal to 0, and when I do that, right, we end up getting that Y equals to 3. So right now it's behaving very functionally. One thing in, one thing out. If you want to make sure, do it again, right? So Y plus 1 squared equals 3. Subtract 1 from both sides, we end up getting that y is equal to 2. One thing in, one thing out. So after a couple of test runs, this feels like it's behaving like a function, right? We've proven that 1x creates 1y. We are a function. Okay. Next one, again, here's the relationship x plus y squared equals 4. So again, input is x, so let's try something. Let's let x equal 0. When I do that, we get y squared equals 4. Like we saw in a few chapters ago, we introduced a square root, which introduces a plus minus. And right away, we can see one thing in, we get two pieces of output. So this is not a function, right? Input 0 creates two outputs, and that makes me non-functional. We don't have to test anything anymore. As soon as you find the one that works or it doesn't work, you ruined it for everybody. Okay, and that's why you probably should try at least 2 or 3 just to make sure, yeah, this is, you know, the rhythm's the same. I keep putting it in, subtracting it, and getting y by itself. Here we put something in, and right away, because of the square root property, we didn't get, you know, we got y by itself, but we got 2 of them. So not functional at all. All right, I looks like a train wreck, all right, but don't be scared. Just follow the rule, right? Let x equal something. So how about I let x equal 0, right? And so when I do that, I get 0 times y minus 2y equals 0 plus 1. Anything times 0 is 0, so we get minus 2y equals 1. Divide both sides by negative 2, and we end up getting negative a half. So one thing in, one thing out. Seems to be behaving like a function. Just to be sure, right, let x equal 1. We get 1y minus 2y equals 1 plus 1. That's a negative y equals 2. Divide both sides by negative 1. We get negative 2. So this is definitely behaving like a function should. 1x creates 1y. Alright, and so we just get that feel from plugging some things in. Right, I did it a couple times just to make sure. And if you want to do it a third time, I guess you could, but this is definitely behaving like a function, despite the fact that there's y's all over the place. Again, hopefully you're seeing this definition, right? Just use the definition. One thing in, one thing out. Whether in any schematic, in any table, in any ordered pair, in anything, we're basically doing that. Now the next one's kind of unique, right? Because there's no x and there's no y, all right? But there's h's and t's. And this is where we come back to the idea of dependent. H, right, is all by itself over here. So h is basically the dependent variable. It's basically y, right? And then t is behaving like an independent variable would, right? There's some formula with regards to t. You give me t, I'll give you h. So t is behaving like the independent variable x, all right? And so again, this is input and this is output. So we'll just begin by letting t equal to 0. And when I do that, we end up getting that h equals negative 6. One thing in, one thing out. So far it behaves like a function. Let's just test it one more time. If t was equal to 1, and I did the math, 1 minus 1 minus 6, we get negative 6 yet again. All right, and so this seems like it's behaving like a function. 1t creates 1h. All right, and that is very, very functional. All right, so that's how we basically test whether a relation is a function. We test the theory. Can I put one thing in and get one thing out? If you can, you're a function. If you can't, you're a non-function. You're just a good old relation. Again, everybody's a relation, but functions are special. They have that simple, that nice one thing in, one thing out relationship. Okay, so onward and upward, we're going to consider domains and range next. See you guys then.